This particular section is relevant to the lab that we will do on this subject. We'll be mapping out equipotential surfaces, and we'll be talking in the lab about the relationship between these equipotential surfaces and the electric field. What does equipotential mean? Well, potential is the word that it refers to the electric potential or the voltage. Equa means equal, the same. So these are surfaces over which the electric potential does not change. And so this allows us to get a little deeper in understanding about the topological landscape, and some of the things that you'll see in this section will remind you of topo maps, actually, and the lab itself will look a lot like that as well. All right, let's define an equipotential surface. An equipotential surface is a surface on which every point on that surface is at the same electric potential. Happy day. That's pretty much simple deal. The net electric force does no work on a charge as it moves on an equipotential surface. Why is that? Well, if the 2 points, let's say we're looking at points A and B here, and they are on an equipotential surface. So let's first understand this diagram a little bit better and then get back to this example. We've got a positive point charge Q here. The electric potential near the charge is going to be big, right? And as you get further and further away from it, it'll get smaller and smaller. We know that from this relationship. As R gets bigger and bigger, the potential gets smaller and smaller. But this relationship depends only on R. It doesn't depend on the angle that we're looking at. So if we look at a bunch of different points at the same distance away from that point charge, all the same distance away, they should all have the same potential. So this sphere is an equipotential surface, this small sphere here. Let's just call that R1. So all those are the same value of R. So there's a take-home message. A sphere centered on a point charge is an equipotential surface. Okay, well, any sphere actually of any radius is a potential, an equipotential surface. Here's another one, R2, radius R2. How does the electric potential of this outer sphere compare with the electric potential of the inner sphere? You say, well, I know the answer to that because we talked about the potential being higher near that positive point charge. So this will be at a lower value of the electric potential, and this will be at a higher value of the electric potential. Now, to come back to this one and to prove this statement that the net electric force does no work on a charge as it moves along an equipotential surface. Why is that? As I move from this point, well, first the statement, what is that? As we move from this point to this point along that equipotential surface, I don't have to do any work. It's free, totally free. How do you know that? Well, to review, the help is that we can review this concept, 19-3, the relationship between the electric potential difference and the work. So this is the key here, and it's just a review. That's why I didn't put a red box around it. It doesn't have a red box. It isn't a new concept. It's a review of an old concept. So this relates the potential difference, delta V, right here, to the work done by the electric force as you go from point A to point B. Well, let me just write this down again. Delta V is VB minus VA. And that's supposed to be equal to minus the work done in going from A to B divided by the charge. Can we find the work done by the electric force in going from A to B? Well, we sure can. If they're on an equipotential surface, if A and B are on the same electropotential surface, same equipotential surface, sorry, and we move along that surface in going from A to B, we know that the potential at A equals the potential at B. How do we know that? It's an equipotential surface. The potentials are all the same. If VA equals VB, then VB minus VA is 0. They're both equal. You subtract one from the other and they're both the same and you get 0. And that says, therefore, that the work done on a charge is 0. There's no work done on a charge as it moves along an equipotential surface. Pretty cool. 19-9. State the relationship. We're getting near the end here. State the relationship between the electric field and the electric potential. All right. Well, let's see about that. In the last chapter, we talked about the electric field for both positive and negative charges. Remember, we said that if the charge is positive, then the electric fields come out of it, emanate from it, begin on positive charges. If the charge is negative, then the electric fields come into it. Several concepts from the last chapter on that. So here's those same electric field lines for a positive charge. They emanate from it, they begin on it, they start at the positive charge and go out to infinity. Well, we know that, as we talked about before, this smaller radius sphere here around that point charge is at a higher potential. And then the larger radius sphere is at a lower potential. And so that's this is the basis for this concept right here. And you can get it from all the previous concepts we've already done. The electric field points in the direction of decreasing potential. How do you know that? Well, here's the direction of the electric field. What direction does it point in? It points from higher potential to lower potential. As we get further and further away from that point charge, the potential gets lower and lower and lower. Or does it work in the other directions? Well, it sure does. I'm going now in the direction of the electric field going at this angle. I'm going from higher potential to lower potential. So the electric field points in the direction of decreasing potential. And that's one to take home with you when we do the lab. But if you could just remember this one, it'll help you a lot in studying these problems. The electric field points in the direction. If you're going in the direction of the electric field, if I just tell you, okay, that's the direction of the electric field, then you can say, Dr. Edwards, if I'm moving in the direction of the electric field, I know the potential must be decreasing. And I'll say, you're absolutely right. That's exactly right. So what else? The electric field is perpendicular to the equipotential surfaces. Notice here that these angles are always right angles. There's an equipotential surface, it's a sphere, and that electric field is perpendicular, puncturing right through that surface of the sphere. And so they're always perpendicular, and its magnitude is given by delta V divided by delta S. So that's new, and this is a relationship between the electric field and the change in the potential and the displacement. So that's a distance. It's measured in meters. Displacement in the direction of the field. So we will always take this delta S to be in the direction of the electric field. And I encourage you to do the same in the lab. When you're thinking about things, figure out what the direction of the electric field is, and then move in that direction a certain distance, delta S, along that electric field line. Then delta S will be a positive displacement in the direction of the field. Delta V, this should say delta here, except for these icons here. So that's delta V, is the associated potential difference, which will always be negative. All right, well, you say, well, hang on, Dr. Edwards, that doesn't make sense. Why is it always negative? Let's say that we want to go from point A to point B. I'm going to go in this direction. Am I going in the direction of the electric field? You say, yeah, sure. We talked about that before. Great. So we're moving in the direction of the electric field. Delta S is this displacement in the direction of the electric field, going from point A to point B. Let me just put a little arrow on here to remind myself that that's the direction we're moving. All right, well, happy day, because I now know that the potential difference VB minus VA has to be negative. Why? Because we're moving from higher potential to lower potential. So the final potential has to be less than the initial. And delta V, is final minus initial, has to be a negative number. So that delta V will always be a negative number. So the happy thing about that, let's just say that the difference, let's just give some actual numbers so you can understand what I'm talking about. Let's say this is at a higher potential. Let's say it's at 50 volts. And then this one, the outer one here, is at a lower potential. Let's say it's 25 volts. Okay? So what's the potential difference? The final minus the initial. Delta V is VB minus VA. VB is the potential out here at the larger radius sphere. That's 25 volts. VA is 50 volts. What's the difference between them? 25 minus 50, well, that's negative 25. Is that a negative number? Well, sure enough it is. It's a negative number. And then, if this distance, for example, let's just say that this distance is 2 meters, delta S equals 2 meters, and you'll do this in the lab. You have those distances, you have the potential differences, et cetera, et cetera. That distance, delta S, the displacement, is always going to be a positive number. We plug those numbers in here. There'd be a minus sign here. Delta V is minus 25 volts. And delta S is 2 meters. So what happens here, the two minus signs cancel each other, and we get 25 volts divided by 2 meters. That's 12.5 volts per meter. And that gives us the electric field. But you say, hang on, volts per meter is not the units of electric field. I say, good point. Where we introduced the electric field and defined it in chapter 18, we said the units for the electric field are newtons per coulomb. Yet we've got an answer here that's in volts per meter. Turns out they're exactly the same. And here's the proof. A volt, as we said before, is a joule per coulomb. So we replace the volt in here by a joule per coulomb. The meter comes along for the ride. Well, what's a joule? Well, a joule, if you remember from last semester, is a Newton times a meter. So there's my joule. The coulomb and the meters come along for the ride. The meters cancel now, and we get that 1 volt per meter is 1 Newton per coulomb. So bottom line is that you can measure electric fields in volts per meter. You can measure them in newtons per coulomb. In fact, the more standard way of measuring them is volts per meter. You'll see that more often. Let's see. All right, we've just proved that. That takes care of that slide. What we're going to do is to verify 19-9C, this equation right here, for a parallel plate capacitor. So E is minus delta V over delta S. Here's the proof. I'm going to just do this reasonably quickly. I'm not expecting you to know this proof, but this is to help you become a believer that this equation is actually right. Concept 19-3 says that delta V is minus the work done from A to B over Q naught. From last semester, we know that the work done is a force times a displacement, delta S. And then the Q naught comes along for the ride. But the force from last semester is Q times E. The electric force on an object is the charge times the electric field. And this is the concept that dealt with that one, 18-9. So I've just replaced the force by Q times E. The Q's cancel each other. This one cancels that one. We get minus dE times delta S. And then we simplify and solve for E. To solve for E, I'm going to multiply both sides by a negative sign. I'm going to divide both sides by delta S. And we get that E is minus delta V over delta S. So that's where that comes from. That's a justification for it. All right. Let's take a look at our electric dipole. Happy day. You get to see the electric dipole again. Beautiful. So pretty. I've marked here that this, first of all, these red lines are electric fields. Let's verify that those look like what we talked about in Chapter 18. In fact, they do. The electric field lines are coming out. They begin on this positive charge. They come in to the negative charge, and it looks just like the diagram that we discussed in Chapter 18. So that's a happy day. What about the electric potential surfaces? The equipotential surfaces, EQUI, these are the surfaces where what? Where the potential is the same everywhere on that surface. So this blue circle here is an equipotential surface. In fact, it forms a spherical, kind of, actually not quite a sphere. It'll be a little bit squashed in the middle here. But if we extend it out into 3D, it'll come out this way. Well, we know what the equipotential surfaces look like for a single point charge. This single point charge has equipotential surfaces around it. If we just ignore the negative charge, single positive charge, the equipotential surfaces are spheres around it. We just talked about that. But as we get further and further away, these electric field lines are no longer directly away from this positive charge. And to follow the rules of relationships between equipotential surfaces and the electric fields, those surfaces always have to be perpendicular to the electric fields. So you see that here. That red line crosses the blue equipotential surface at a right angle. Everywhere here that's true. And I've also marked where the high potential is, high electric potential, and so this is a high electric potential surface. Has a high electric potential. And this one has a low one. In fact, it's negative, right? We show that that electric potential near this guy is going to be negative. So definitely low and actually negative. It's that low. What about here? So this is high and positive. This is high and negative. It's low and negative with its magnitude opposite this positive electric potential here. What would you say the electric potential is going to be right here? Here it's positive, here it's negative. You're right. It's 0. I think some of you got that. It's hard lecturing to a camera. But right here, it's going to be just halfway between those two. And just like the example we did with the positive charge on one side and the negative charge on the other side, we actually worked this out a couple of examples ago where right smack dab between the two, we ended up with an electric potential that was 0. All right, so this one is directly pertinent to the lab. So just to help you with this lab, the potential difference between adjacent equipotential contours is 2 volts. So this is an equipotential contour. We call them surfaces, but actually it's a contour because we've cut through the 3-dimensional ones. Okay, and this is where it starts to look like topo maps. What we're told here is that the potential difference between adjacent equipotential contours is 2 volts. So, for example, if this one was, well, let's just say this one's, we know this one has to be 0 volts. So that makes that easy. So what would this one be at if it has to have a difference of 2 volts? Well, we have to be moving in the positive direction, right? Because we're heading over toward that positive charge. So this one have to be the electric potential at this blue equipotential contour have to be 2 volts. What about this one? Difference is 2, that has to be 4. This has to be 6 volts, etc., etc. All right. So now, what would this one have to be? Just to see if you're getting the right idea. What does that one have to be? Yep. Minus 2 volts, minus 4 volts, minus 6 volts, etc. Perfect. Now, the problem that's related to the lab. Estimate the electric field at the 2 locations shown. So here's the first location that I want to estimate the electric field. I know the potential difference here is 2 volts. And I'm interested in finding the electric field at this point here. So technically the electric field is going to be valid, most valid, right halfway between point A and point B. I'm choosing a displacement, delta S, that's in the direction of the electric field. We talked about that before. Here's the electric field coming out like that. That's the line that I'm interested in. I'm going to do my displacement from A to B in the direction of the electric field. Okay, happy day. And now I need to know what the change, and according to the concept that we just covered, the electric field at that point is the negative of the change in the electric potential at that point divided by the displacement that you're undergoing from point A to point B. Well, let's do the displacement first. And what you'll be doing in the lab is similar to this. We'll use a scale. So this is the scale of distances. And it's measured in meters. So this distance right here is 0.1 meter. Well, that happens to coincide, and yeah, I put that in this way to make it easy. It happens to coincide with this, approximately with that distance between here and here. So let's put in a displacement of 0.1 meters. And now let's ask about the potential difference between point A and point B. So this is VB minus VA. Well, we can actually do it because we actually figured out what the potential at all these surfaces is. This is 0, this is 2 volts, this is 4 volts, so that's the potential at point B. This is what? 6 volts, potential at A. So delta V, we put it down here, is VB minus VA. VB in this instance is 4 volts. VA in this instance is 6 volts. So we get minus 2 volts. Should we be embarrassed that that's a negative number? No, we shouldn't, because we expected it to be a negative number. I told you that if you're going to move in the direction of the electric field, the electric potential is going to go down. All right, so we put in a negative 2 volts here. We got a negative sign from here that came along for the ride. Those two cancel each other like I promised you they would. And then we get 2 divided by 0.1, which is 20 volts per meter. Is volts per meter a legitimate unit for the electric field? And you say, yeah, sure enough, it is. 20 volts per meter. Happy day. What about at the second point? Same kind of thing is going to happen. What are we going to get for delta V between this point A and this point B? Well, these are equipotential contours or surfaces, and so anytime you go between any two adjacent equipotential contours, you're going to have a difference of minus 2 volts for this particular case. So you get a minus 2 volts, but now the distance is about twice as what it was, so maybe about 0.2 meters, and you get 10 volts per meter. So does it make sense to you that the electric field at point 2 here should be less than the electric field at point 1? And you say, well, yeah, maybe so. Point 2 is a little further away from that positive charge, so the electric field should be decreasing. And I say that's a great argument. The other way to think about it is that the closer that these, remember when we talked about in the last chapter where the electric field lines, these guys here, the red ones, where they're close together, the electric field is high. Well, here the electric field lines are spreading apart more. The electropotential, equipotential surfaces are also spreading apart further. And so this delta S2 is bigger than delta S1. And if you have a bigger denominator, then you have a smaller number. So that's why we're getting a smaller and smaller number there. Yeah, I think that one takes care of that problem. Oh yeah, the other thing I was going to say about this, this looks like a topo map. with this being a peak. So, and with the electric potential playing the role of elevations. So you can think about this as 0 feet above sea level. And then this is 2 feet above sea level, and 4 feet above sea level, and 6 feet above sea level, et cetera, et cetera. And you're getting higher and higher as you approach the tip of this mountain. Whereas down here, what would this be in a topo map? Well, this would be Death Valley, below the below sea level. So you're talking about a depression here. So if you try and visualize this in 3D, this would be a cone, maybe a volcano-shaped cone, because it comes up and gets really steep here. And then this would be a deep, deep lake or an ocean that where the elevation's getting less and less and less as you fall further into that hole. The drawing shows 3-point charges of equal magnitude. Okay. Point plus Q, minus Q, and minus Q. So these two are negative, and this one's positive. Some of the equipotential lines surrounding these charges are shown. So there's another word that we use: equipotential surface, equipotential contours, equipotential lines. They all mean the same thing. You're drawing a path where the potential is constant everywhere along that path. All right, and 5 are labeled using the letters A, B, C, D, and E. So these are these letters you might not be able to see. What is the direction of the electric field at the location of letter D? So here's D. Well, good question. What do we know? We know that electric field lines point away from positive charges and point toward negative charges. We also know that electric field lines are perpendicular to equipotential surfaces. We also have an equipotential surface right here, or an equipotential line. So that's an All right, so put it all together. What direction, you just try and point with your finger, what direction does it go? You know the electric field has to be perpendicular to this surface. So it has to either go this way or that way. And what direction it's going to be? And you say, well, yeah, it has to be toward the negative charge because electric fields always point toward negative charges. So the electric field has to be this way, toward the negative charge. Okay, it's starting to come together. Let's see if we can find an answer that works. Perpendicular to the equipotential line marked D and directed toward the negative charge closest to it. Yep, that's the one. Why is this not true? Why could the electric field not be parallel to the equipotential line? Well, they have to be perpendicular, so that won't work. Perpendicular to the equipotential line marks D and directed toward the location of the letter A. So we're saying this direction. Well, that can't be because we know that the electric field lines point toward the negative charges. And toward the negative charge in the lower part of the drawing, over toward this one, well, it can't be because they have to be perpendicular toward the positive charge. Okay. All right, the plates of a capacitor. We talked a little bit about them so far. We'll talk a lot more about them before we're done. And in fact, in the very next section of the book, we'll talk about capacitors in more detail. The plates of the capacitor are separated by a distance of 0.032 meters. That's that distance here. And the potential difference between them is negative 64 volts. So here's A, here's B, and VB minus VA is minus 64. So just so we don't get confused, sometimes it helps me to rewrite this. If we add VA to both sides, then we'll get VB minus VA plus VA gives VB. We've added VA to the right side, minus 64 volts. Which one's higher? Which one's lower? Well, VB, if you take whatever the electric potential is at A, you have to subtract something from it to get the electric potential at B. In fact, that something is 64 volts. So whatever VA is, you have to subtract 64 volts from it to get VB. So VB must therefore be at a lower potential, and BA is at a higher. And you say, well, I could have guessed that right off the bat, Dr. Edwards, because look at this. There's positive charge there. We know that the potential is high where there's positive charge. Happy day. Good for you. So between the two equipotential surfaces shown in color, there's a potential, so these are two equipotential surfaces. We're calling them little a and little b. And there's a potential difference of negative 3 volts. So VB, little lowercase b minus lowercase a is negative 3 volts. Again, that minus sign says the same thing that the minus sign did right here, that the V at little b is lower. The electric potential at little b is lower than the electric potential at little a. Okay? All right, find the spacing between the two colored surfaces. So we want to know this distance here. And we're actually going to call it delta S. Delta S is shown here as well as here. So let's actually work it out. First of all, this first step here is to find the electric field, magnitude of the electric field between here and here. And that's given by this concept that we've just been talking about, a negative delta V over delta S. The potential difference between these two is negative 64 volts. That minus sign kills this minus sign. The distance is 0.032 meters, and that gives an electric field of 2 times 10 to the 3, 2,000 volts per meter. Well, so now we're interested in finding out the distance between these two, that the separation between these two smaller guys. And the way that we can do that is using this exact same equation. E is minus delta V over delta S, but solving that for delta S. And how would you solve that for delta S? Well, if we multiply both sides of this equation by delta S, so this is exactly the same as that, but I've just multiplied both sides by delta S. And the reason that I did it is to get this delta S to cancel that delta S, and to solve for delta S. But if I want to solve for delta S, I'm going to have to also divide by E. Divide both sides of the equation by E. And the reason I did that is so that these e's will cancel, and we get delta S. That's a delta, it doesn't look much like 1, equals minus delta V over E. Well, that's this equation here. So that was the derivation of that equation. I would never memorize that equation, just do the algebra yourself. So we're told that this is A and B up here that we're talking about for this equation. And this is little a and little b down here. We're told that the potential difference between those two is -3 volts. And we're going to use the same electric field here as we did up here. So hang on, how can you justify doing that? How come those electric fields are the same? And the answer is the electric field between two parallel plates, one positively charged, one negatively charged, is uniform. Talked about that a little bit before. All these electric field lines are straight, equally spaced. The electric field is uniform. So whatever the electric field is between here and here is also the same as the electric field between here and here. What will change is the potential difference, the electric potential difference. Between here and here we have 64 volts, or -64 volts. Between here and here we have -3 volts. But we have the same electric field everywhere through. It's uniform. Everywhere you look at it, it's the same. Okay, plugging in that electric field, the minus signs again cancel each other, and you get 1.5 times 10 to the -3 meters. So compared with 0.032 meters, 1.5 times 10 to the -3 is quite a bit smaller number. That's an example.